So if we look back over the last couple of our lectures, we see that there's sort of been this common theme. When does something converge? And everything we've talked about so far has been when we've had terms which are always positive. So we're going to talk about another test today. This is sort of our last day of convergence test. And so let's enjoy it. And this is probably one of the funnest tests. It's also one of the easiest. It's called the alternating series test. And how does it work? Well, it says, suppose that you do have a sub n is your sequence of positive numbers, and they go to 0. So here you see weakly decreases. It just means that, one term is bigger than the next term, is bigger than the next term, and so forth and so on. So if you were to graph it, your terms are going down. So your terms are going down to 0. The conclusion is that your sum, -1 to the n, a sub n, converges. So why do we call this the alternating series test? The alternating series comes from this part right here. So the idea is we're alternating sign. So positive, negative, positive, negative. Now, how does this work? Well, the idea is you start here. So this could be, you could think of this as a value a0, if you like. Now, what happens is after you have a0, you're going to go back to the left. Because you can think of it, a positive number says move to the right, a negative number move to the left. So a0, move back, or a1. So really, this value here, at that point, that's a0 plus a1. And so what happens is this little arc says we move to the left. Oops, it's not a0 plus a1, ah ha 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 ha, a0 minus a1. That's alternating sign, right? And then we move back. So that this point right here is our a0 minus a1 plus a2. So what happens is we move back and forth. Now, the key thing is, you see how we're going down? So that when I move back to the right, I'm never going to get past a0. And if I move again, I'm going to move again. I'm never going to get further to the left of where I started. So what's happening is I'm moving back and forth. But because my terms are getting smaller and smaller, the amount I move back and forth gets again smaller and smaller. And then eventually I have to settle in on my limit L. So one of the things that we have mentioned at least once before, and we haven't spent a lot of time on this, but partially because, well, it takes a little bit of work to think through all the details. But let's talk about error. Now what we mean here is we say, well, look, suppose we're looking at some sum, and -1 to the n of a sub n, and we know it equals L. Okay, so that's the question. But the question really says, suppose I want to get a good estimate for what L is. How far off am I? So suppose I start at capital N and I go to some number. I'll call it capital Q. I just need some number. All right. Plus, there's an error term. Now the error term is everything that's left. So that would be starting at the next term and going to infinity, -1 to the n, a sub n. So here, this is our error term. How far off we are from L. Now, how far off could we be? And here's the fun thing. If you think about the picture, and the picture really helps us in this situation, is if I'm at a particular value. So let me use my highlighter here. So if I'm at a particular value, and then I follow that to my next value, my value for L has to be somewhere in between. So what does that tell me? Well, that tells me that if I stop here at Q, I want to say, well, how far off from L could I be? The answer is the next step. So it turns out that my error is at most the size of a cubed plus 1. So if I have something alternating and I want to say, well, how far off am I? I'd have to say, well, how big is the next term? And that's a bound for my error. So this is a good way to make sure that when we're adding terms up, that we can get something pretty quick. So for instance, suppose I have something that looks like the following. So sum n equals 0 to infinity of, say, negative 1 to the n over 2n factorial. Now, this turns out to have an interesting interpretation. We'll get to this later on. But if you were to write down the first few terms, you get negative 1 to the 0 over 0 factorial, which is 1. And then the next term would be negative 1 to the 1, which so it makes it a minus, over 2 factorial, well, that's over 2. The next term will be negative 1 squared, which is plus 1 over 4 factorial. Well, that's 24. So that's 2 factorial. That's 4 factorial. Now the next term after that, that would be n equals 3. Negative 1 cubed means it's a minus. 6 factorial? Yeah, exactly. Big number. To get 720. So that's 6 factorial. Now, suppose we ask the question, let's just say I had to stop there. How close is this to the true answer? All right, so we can say really it's an approximately that. And we can say, well, the error is at most, well, what's the next term? Ignoring the sign, so we don't worry about the sign. So the error is at most 1 over 8 factorial. Now, how big is 1 over 8 factorial? Well, you have to be really patient, but the way you get to it is you multiply 6 factorial times 7, which would give you 5,040. Then if you multiply that by 8, that would give you 40,320, which that's a pretty small number. So just adding up just a couple of terms, our error is fairly small. Now, the reason it works so well here is, of course, 2n factorial goes to 0 very quickly. But this gives us a really simple way to make sure our error is very small. If they'd all been pluses, it would be a little bit more challenging to figure out what to do with the error. But that's one of the advantages of the alternating series test. All right, so the key idea. Do I go to 0? And I have to go strictly down to 0. Do I alternate sign? So there's really two things to check. Alternate sign, plus, minus, go to 0. And if I do those two things, life is good. Okay, so let's talk about the questions. Determine if the following converge or diverge. All right, well, 1 over n squared. Converge or diverge? What's the answer? Well, can we use the alternating series test? And no, we can't. Why not? Well, notice there's no changing of the sign. So since there's no change in sign, it doesn't apply. Well, is there anything else we know? Well, there actually is something we know. That's not just any series, that's actually something we've seen before. So this is a p-series, and because it's a p-series, we know when p-series converge. So does this converge or diverge? The answer is, it converges. So that's good. All right, the next one. Negative 1 to the n over n squared. Does this converge or diverge? Well, we can think of this as negative 1 to the n times 1 over n squared. So if we were to rewrite this, that's the sum 1 to infinity, negative 1 to the n times 1 over n squared. So just the alternating part and the other part. So the question is, okay, I alternate. Does that part go down to 0? And it does. And so we can say, all right, alternating series test. And so therefore, what's our conclusion? The conclusion is, yes, converges. Good. Okay, all right. Now, the next one. 1 over n. Oh, that's a famous one. That's a famous one. Now again, not alternating, but does this converge or diverge? And the answer is, well, it diverges. Now, do you remember why? This one actually has a name. What is it called? It's harmonic. So this is the harmonic sum. And for the harmonic sum, it diverges. So it's that sum that grows very, very, very slowly, but it diverges. Now, this one, what does this look like? Well, again, if you really wanted to, you could think of it in the following way. Namely that there's this alternating part and this 1 over n. So I change signs, plus and minus. This part goes to 0. So, does it converge or diverge? Well, we check the alternating series test. And here we see, all right, alternates in sign, this term goes to 0, and therefore our conclusion is it converges. Good. All right. Now, how about this sum? N equals 1 to infinity of n. So that's 1 plus 2 plus 3 plus 4 and so forth and so on. Does that converge or diverge? And how do we know? Well, this is going to diverge. Now, how do we know that? Well, we can do an nth term test. Because if we look at the terms, they get bigger and bigger. So this diverges. But maybe if we alternate sign, right? So now, negative 1 to the n times n. Does that converge or diverge? And how do we know? Well, it does alternate sign, but it's not enough to alternate sign. You've got to also make sure your terms go to 0. So negative 1 to the n times n. Do our terms go to 0? No. If the terms don't go to 0, you still have the nth term test. See, if the terms don't go to 0, it doesn't matter whether it's going to a positive number or a negative number or it's alternating, it's still going to diverge. So you see we can have sort of several different types of phenomena. We can see where it converges regardless of whether or not we have that alternating sign. We can see it diverges whether or not we have the alternating sign. And then we can sometimes see that the alternating sign can be really useful. And so we want to sort of distinguish between these different phenomena. So we have some names for this. So here we go. So the three possibilities for a sum. First thing is that if I take away the sign, so in other words, I assume everything is the positive version of it, then it still converges. We call this absolutely convergent. And so when it's absolutely convergent, the absolute here, you can think of it as we're taking the absolute value of every individual term. There's also conditionally convergent. Conditionally convergent says, well, it does converge, but you really need to somehow have that negative coming into play. In other words, if you take out the negatives, which is what happens when you take the absolute value, that diverges. And so you need the negative. So that's conditional convergence. And that's kind of, there's something really odd that happens with that we're going to talk about in just a couple of minutes. And the last possibility is just like, all right, it doesn't matter. It just diverges. There's just no hope. All right. So, what do you have? Now, there is a nice fact which says, hey, if the absolute value of the terms converge, then the sum of the original values converge. So that's why when we came up here, we didn't say, well, maybe the terms diverge, but the absolute value of the terms converge. No, that can't happen. So it has to be the case that if the absolute value of the terms converge, then the sum of just without the absolute value converges. All right, so let's now, with this extra sort of refinement, we've given ourselves more terms. We can say, look, no longer are we diverging or converging, where we either diverge or we converge in two different ways. And between the two of them, absolutely convergent is the better version of that. Again, we'll get into why in just a second. So, the question. I have here 3 different sums. Are they absolutely convergent, conditionally convergent, or divergent? Okay, so let's start with the first one. The sum, 1 to infinity, negative 1 to the n over 2 to the n. Now, you will notice here that this is an alternating sum because you have that negative 1 to the n, making it plus, minus, plus, minus. So you might say, okay, all right. Whenever I see an alternating sum, maybe that means I can only be conditionally convergent, but that's not at all the case. Conditionally convergent just says, all right, you do need the negative. It's not that it's not the case that just because you have negatives, it means it's conditional. So if we stare at this for a second, though, we can say, hey, it looks a lot like a geometric sum. Now, the reason it looks a lot like a geometric sum is because it is a geometric sum. And so this sum converges. So converges because it's geometric. Now that's not enough to say that it's conditional or absolute. It just says it's one of the two. We also need to say, well, let's look at the sum where we take away the alternating part. So that'd be 1 over 2 to the n. Now, does this converge? Well, this also converges. And why does that converge? Well, again, same reason. It's geometric. And in this case, it's geometric. And what we multiply by it every time is multiplying by half. So both the original sum and the absolute value of the sum converges. So that puts us into our first category. So this one here, this is absolutely convergent. No questions asked. Okay, good. Good. Well, now let's go try the next one. Sum of negative 1 to the n over square root of n. All right, does this converge? Well, notice we do alternate the sign because of that negative 1 to the n. Here, because we're dividing by square root of n, as n gets bigger, our terms get smaller, and they're going to 0. So, alternate sign, terms go to 0. Our conclusion is converges. And what's our reasoning? Well, here we have alternating series test. All right, good. Now, are we done? No, because just because the sum converges doesn't say what kind of way does it converge. Is it absolute or is it conditional? So now we take the absolute value, which is another fancy way of saying get rid of that negative 1 to the n. All the terms are positive. 1 over root n. Or if you like, that's still another way to write that, 1 over n to the 1/2. Now, does that converge or does it diverge? It diverges. Why does this diverge? Well, what is it? It's a p-series. And we know exactly when p-series converge and when they diverge. So, we see, aha, the sum converges, but when we take away the signs, it diverges. That means we're in our second type of arrangement here. So this right here, this says this is conditional, or conditionally convergent. All right, so we need the negatives. All right, last one. So the sum, n equals 2 to infinity, sine of n over n log n squared. Now, this one is kind of a interesting case. Makes you want to say, huh. So let's ask a couple of questions. Do the terms go to 0? It's actually true that the terms go to 0 because you can see that upstairs sine of n is not going to be very big. It's always bounded. Downstairs, it goes to a large number and gets bigger. Log n gets bigger, so it does go to 0. But does it go to 0 in the right way? And the problem is no. And before we talk about why, let's ask the other question, is this alternating? Well, notice what we have in the numerator. Upstairs we have this sine of n. Now what's true about sine of n? Well, what's true is that sine of n, it's going to change signs. But it does it in sort of a very inconvenient way. So if you were to graph the sine function, and it looks something like a sine curve. Okay, so there's the sine curve. What you'll see is that when you graph what sine of n looks like, it does something more or less like this. And because this is not sine at every value of x, it's only sine at the integers. And so you're kind of sampling. So you occasionally will get a couple of terms which are negative in a row, and then a couple of terms which are positive in a row. The other thing that's happening is sometimes you'll get a term which is very close to 0 in the output, then the next term will be fairly large. So the other thing that's happening is, first off, it's not alternating sign. In the long run, you get positive terms and negative terms, but it's not strictly you're positive, the next one's negative, and you go back and forth. And the other problem, it doesn't strictly go down to 0. It's possible it might waver a little bit, so that one term is a little bit smaller than the next term in size. So this means that the alternating series test doesn't apply. So there's no conclusion about that series. So cannot use alternating series test. Now, the bad news here is almost all our other tests for our sum, we can't use anything that's negative. And sine will be negative. It does show up. So that means that as the sum exists right now, we can't make a decision. But, okay, we're not done yet because we do have to give an answer. And I will say, by the way, even after today, we are not going to be able to answer all questions that we might encounter. There's still a lot left to do. Math is a big subject. And almost always we can say, all right, we can answer that problem, but can we answer this one? And, well, it doesn't take a lot to stump us, temporarily. We're always curious. So, let's look at the absolute now. So let's take a look at the absolute value. Now, the only place we need the absolute value is to look at absolute value of the sine, because that's the only part that can be negative. Absolute value of sine of n over n log n squared. Now, here's sort of our thinking. Whenever you see a sine or a cosine, sort of two things can happen. If it's something like sine or cosine where the inside is really nice, like a multiple of pi showing up, well, that says that, hey, this is really clean and I actually am just obfuscating facts. And then we can replace it by some simpler expression. That's not the case here. This is the case where we have, all right, it's a weird thing. Sometimes it's positive, sometimes it's negative, and it's hard to predict the value. So in the case when we have something that it's really hard to understand what the value is, we can use the following fact. And it's a really cool fact, and it says that if I look at the absolute value of sine, it's almost 1. So if we think about it as comparison, we can say, well, look, if I look at this sum, it's certainly going to be smaller than the sum where I take the part that's bounded and replace it by what it's bounded by. So 1 over n log n squared. Now, does that sum converge? Because if this second sum converges, which is a little bit easier to work with, this sum would converge. And if that sum converges, then the conclusion is that this sum converges. Why? Because if we can take the absolute value of it and it converges, the original sum converges. Well, what do you think? Does it converge or diverge? If it was just the 1 over n, that's harmonic. That wouldn't converge. But there's this little teeny tiny bit trying to nudge it. Does it nudge it just enough? And how can we figure that out? It would be really integral to solving this problem if we had a test that we could use. So, is there some test which would help us to figure out the answer? Something that could help us get through this integral part. Yeah, we can use the integral test. Exactly. Good. Okay. So, look at the integral from 2 to infinity of 1 over x log x squared. Which, by the way, the integral test at this point is almost always going to look like something like that. All right. Now, if we do a little quick substitution, u equals log of x, du equals 1 over x dx, then lo and behold, this becomes the integral log 2. Now, as x goes to infinity, u goes to infinity, because log of x tends to infinity. So this becomes log 2 to infinity. The 1 over x dx becomes du. Then 1 over log x squared becomes 1 over u squared, u to the minus 2. Well, that means that this has a nice antiderivative. It's minus 1 over u from log 2 to infinity. And the nice thing is, as I head off to infinity, this heads to some finite value. So, I'm going to move up just a little bit. So this is converging. So when I talk about this is converging, I mean this integral converges. Integral test says the sum converges. Comparison test says this sum converges. And finally, when we take the absolute value, if that sum converges, then this sum converges. This is a very, very long way for us to get to the conclusion that this sum right here is absolutely convergent. And this is, there's a lot of things that go into figuring this out. So you got to be very careful. And of course, there's also things which don't come into play. So you got to know, when can you use a test, when can you not use a test? Because, well, there's subtlety. And we want to make sure we don't get caught up in the subtlety. Now, here's a really interesting and weird fact. And the first time you see it, you're probably not going to believe it. And even though I tell you it's true, you're probably still not going to believe it. But it's true. And here we go. So if I have something which is absolutely convergent, it does not matter how I add the terms together. In other words, if I jumble up the order where I add things up, as long as I make sure I add everything up eventually, I'm still going to get the same answer. So in some sense, absolutely convergent says you can just change the order of addition. This makes total sense, because if I have values of a plus b, that should be the same as b plus a. So this is what we're used to, Let's throw in another a plus b plus c. That's the same as c plus a plus b, or it's the same as b plus a plus c. It doesn't matter. If I add all those up, then I'm always going to get the same answer. Now here's the weird thing. This should make you say, like, what? If it's conditionally convergent. So remember, that's sort of the thing that says you need the negative signs. Then rearranging the order of how we add the terms together can change the value of the sum. In other words, it matters what order you add. So you can get things to add up to any number you want, actually. It's this weird phenomenon. So here's this fun fact. Here's this sum. N equals 1 to infinity, negative 1 to the power n plus 1 over n. Now, if you look at this sum, and here you get 1, minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, dot, 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 dot. if you add them up in that order, it turns out, and we will show this in about a week and a half or so, that it's log 2. All right, but that's if we add it up in that order. Can you add it up in a different order and get a different number? And the answer is yes. And the really surprising answer is you can make it be any number you want, depending upon how you add the terms together. So let's take a step back and try to sort of understand what the intuition is. What's special about absolutely convergent versus conditionally convergent? And why can we get this different phenomenon going on? So here's sort of one way to think about it, is I can think about it as when I'm adding up the sums, so the sum of a sub n is telling me how to move on the number line. All right, so in other words, I can say, well, I start at some place, and this is the same picture that we saw, by the way, at the very beginning today. So you start here at 0, and then the A0, well, if it's positive, it says move to the right. If A1 was positive, then you move to the right again, so A0 plus A1. Now, if A2 is negative, it says move to the left. So you have A0 plus A1 plus A2. So, in other words, where AN positive, we can move right. Where AN is negative, we can move left. All right? Okay, so I'm basically encoding. So for instance here, it says first move to the right by 1. Now move to the left by a half. Move to the right by a third. Move to the left by a fourth, and so forth and so on. Now, here's sort of the interesting part. So if I have a sum which is a sub n, and it's absolutely convergent, I can think about what's happening as really saying, okay, the amount we move to the right and the amount we move to the left. Well, how do I find that? What you do is, this is you add up the positive terms, and this is you add up the negative terms. Okay, so far, this actually has nothing to do with absolutely convergent. It just says, for any sum, the amount I move to the right, you add up the positive terms, the amount you move to the left, you add up the negative terms. And here's the important thing is, when it's absolutely convergent, this thing is finite, and this part is finite. So that the amount I move in either direction is a finite amount. And so at the end of the process, I'm only going to be moving a finite amount. I have only a small amount of wiggle room. If we switch it around though and say, if we are conditional convergent, now what happens? Well, if you are conditionally convergent, what happens? So we come up here like 1 plus a half plus a third plus a fourth, so forth and so on. When you add up the positive terms, what you end up with is you end up with a positive infinity. And when you add up the negative terms, you add up with negative infinity. So in some sense, when something's conditional, what you're getting is you're getting something that looks like this. It looks like infinity minus infinity. And this has this sort of indeterminate form. All right, I can't spell indeterminate. Imagine that was the right spelling of indeterminate. And so what's happening is that you get to move a lot. So you can move infinitely much in the positive direction, which you can say is to the right, and infinitely much in the negative direction, which is to the left. Now, what do we do? Well, what we do is, suppose we have a goal. Let's suppose I want to get to a big number, 137. So I start by moving to the right. And the thing is, even though I'm starting at 0 and 137 is a long ways away, I have infinity to move to the right. So eventually I will pass 137 at some point. Now, as soon as I pass 137, what do? I start moving to the left, and it usually doesn't take me very long to get below 137. Now what? Start moving to the right again, until I just pass it, then move to the left. And so what I'm going to do is, because I have infinitely amount of time I'm going to move to the right, infinite amount of time moving to the left, I'm going to spend most of my time just sort of narrowing wiggling around 137. Now, at the end of the day, I will have moved all the way I can to the right, because I'll have added all the positive terms, and I'll have added all the negative terms. So I'll have added all the terms, but what's going to end up happening is I'm going to get closer and closer to 137, and therefore I can get to 137. Now, there's nothing special about 137. It's just that the fact that I have all this freedom to move, that tells me I can get there. Things like this, by the way, are why mathematicians get really careful and very precise. Because it sounds so innocent, like, oh yeah, it shouldn't matter what order I add numbers in. It's obvious I get the same answer. But whenever you have this infinity minus infinity, weird things happen. And that's why you want to be extra careful. You want to be the right amount of careful. All right, so that's a fun little aside. Okay, now let's try some different things. Next example. Let's determine if the following sum, n equals 1 to infinity, negative 1 to the power n plus 1, log of n plus 1 over n, does it converge? Does it diverge? You decide. Well, no. It's not that we decide. It's like, what does the math tell us? So, this one shouldn't be too bad. What do we see? Well, when you see a negative 1 to a power n, that tells us that we're alternating. Okay, so, alternating. All right, now what else do we have? Well, now that you know it's alternating, by the way, the n plus 1, the only thing that the plus 1 is telling us is that instead of necessarily starting with a minus or starting with a plus, we just sort of shift our signs by 1. But the important thing is that you alternate plus, minus. So then you look at the other piece. Now the question is, what's happening to these terms? So this is our a sub n. And once we know it's alternating, the question is, what's going to happen as we go to infinity of a sub n? So that's the limit as n goes to infinity, natural log of n plus 1 over n. Can you see what that's going to do? If you look at it, you might see it a little bit simpler if we say, hey, this is really log of 1 plus 1 over n, because I can think of it as n over n, 1 over n. And now we say, yeah. See, the 1 over n is going to get small. So in the limit, this goes to log of 1, which is 0. Now, there is a small technical detail which we're going to skip over, because it's an annoying detail, but technically what's something we have to show. We need to show it goes to 0, but we also actually have to show it goes strictly to 0. In other words, it doesn't, oscillate a little bit as it goes to 0. We're going to skip that. You can assume that from here on out, if something goes to 0, it does so in a nice way. Well, modulo maybe one more example today. So, terms alternate, they go to 0. What's our conclusion? Our conclusion is this will converge. Good. All right, why? Alternating series test. Now, you might be tempted to look at this and say, hey, why don't we think about maybe this is a sum we can get our hands on. So let's take a look at what we have. So let's going to swap colors here. do a slightly different color here. Okay, so what do we have? Notice one thing we can do. This is negative 1 to the power n plus 1 times natural log of n plus 1 over n. Natural log, you can actually write that as a minus, right? Division becomes subtraction. Log of n plus 1 minus log of n. So if you write down the first couple of terms, so n equals 1, minus 1 to the 2 is 1. So we'll get log of 2 minus log of 1. Then the next term will be a minus 1 to the 2 plus 1, because the next term is n equals 2, which is a minus. And then we'll have log of 2 plus 1, which is log of 3. And then minus log of 2. And then the next term would be what? Well, minus 1 to the 3 plus 1, because the next term is n equals 3, which would make it a plus. And then it'll be log of 4 minus log of 3, and so forth. Now, you might say, nice. This log of 1 is 0. Okay, cool. And it looks like those might cancel. Do they? All right, good. I like a nice hefty dose of skepticism. Remember, the minus sign will come through. So this minus log 2 is actually a plus log 2. So what ends up happening is you get something like log 2 plus log 2. So that's 2 log of 2. Then you're going to get a minus log 3 and a minus log 3, so that's minus 2 log 3, and so forth and so on. And what you end up getting is you end up with a sort of a sequence doing something. Does it converge or not? Well, we know it converges. It's alternating series test. So you want to be a little bit careful here. Of course, if you write it in this way, you might think, hey, wait a second. This sum right here, is this sum converging or is it diverging? And well, if you actually write down what it is, the 2 you can comes out, and you get sum n equals 2 to infinity, and well, you're going to get minus 1 to the n log of n. Well, does this converge or does this diverge? What do you think? Well, the answer is it diverges. Why? Well, it's negative 1 to the n times log of n. So this is actually diverging here. Now, at this point, you should be making yourself say, wait a second, Steve, you said before, I won't have something which converges equals something which diverges. Well, you should be very suspicious here. Whenever you do a step like this step right here, this is a suspicious step. You have to be careful. When something is a conditionally convergent sum, you don't just want to throw terms around and recombine and say, hey, I can add this to that and everything's going to be okay. Because maybe not. You got to be really, really careful here. So, all right, that's just our word of warning. All right. Be careful. We'll make a little note. Be careful. So, moral is, if something's conditionally convergent, sometimes it's really on a razor's edge. All right. So let's look at this infinite product. Okay. Well, that's different. So we've done infinite sums. Can we say something about an infinite product? So here we have 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7, and so forth and so on. Notice that the numerators are the even numbers, and we repeat it every number twice. 2, 2, 4, 4, 6, 6, 8, 8, 10, 10, 12, 12. The downstairs are the odd numbers. We have 1 once, otherwise it's every number twice. 3, 3, 5, 5, 7, 7, 9, 9, 11, 11. Does this converge to something? Should we expect it to? And what does it mean? Well, one of the ways we can approach this is we can think of it, well, I can think of this as what? Well, I can think of this as, if I think of this as say this is my first term, n equals 1. So this is n plus 1 over n on that term. And here, this would be n equals 2. This would be n equals 3, so forth and on. And notice that here for n equals 3, again, it's n plus 1 over n. For n equals 4, not quite. N equals 5? Yeah, it works out. Well, what's wrong? For n equals 2, it's not 3 over 2, it's 2 over 3. Well, okay, what does that mean? So what's happening there is it's n over n plus 1 if we are the even numbers. All right? So it's sort of alternating. It's n plus 1 over n for the odd numbers, n over n plus 1 for the even numbers. All right. Well, so what's our intuition? So we've been using sigma for infinite sums. What would we use for infinite products? Well, sigma, we think of it for sums because of the s. S is for sum, that's what it means to me. S is for sum, that's what it means to me. S is for sum, that's what it means to me. So what would we use for product but a p, which is pi. So this is a capital pi, and we use that for product. And we can think of it at starting at n equals 1 to infinity of some sequence a sub n. So just as we have infinite sums, we can talk about infinite products. And so what we care about is you say, well, we'll take a limit, say as capital N goes to infinity, of the product from 1 up to some capital N of a sub n. So this is sort of, say, let's just sort of look at this, and does this equal some value L? So that's our question when we ask for does something as an infinite product converge. So just with infinite sums, we have the same type of question. Now we have the challenge of how do we actually go about doing this? And we can go back, take a step back and say, you know what? Let's not reinvent everything. Let's use what we know about infinite sums. Okay, so how do I turn a big product into a big sum? Can I turn a big product into a big sum? Well, I claim the answer is yes. Yes, you can. Now, how do you turn a product into a sum? Spoiler alert, you use logarithms. See, logarithms are really custom built to turn multiplication into addition. So, if I take the natural log of the product from n equals 1 to capital N of a sub n, that becomes, the log of the product, is the sum from 1 to capital N of the natural log of a sub n. So the log of a product is the sum of the logs. That's one of the reasons why we like logs. Now let's think about what's happening. Well, you'll notice here, if n is an odd number, then I look like n plus 1 over n. If n is an even number, I look like n over n plus 1. These are really close to each other. In fact, the only thing that's different is I flip them around. Now, the way you flip a number around is you use a sign. So for this particular sequence, so I'm thinking about here's my A1, here's my A2, and so forth and so on. Well, for this particular sequence, I can say that the natural log of a sub n, that's a sum from 1 to capital N of negative 1 to the n plus 1 log of n plus 1 over n. You see, because when n is an odd number, an odd plus 1 makes this an even. Negative 1 to an even is 1. So we end up with n plus 1 over n. When we're an even number, n plus 1 is odd, so we get a minus. And when we take a minus times a log, it's like we flip the inside, so we get n over n plus 1. So the question about whether or not this infinite product converges is the same as asking, does this infinite sum converge? See, I'm already circling this side here. And we know that this converges because of what we did on the left-hand side, alternating series. And so our conclusion is, it's a nice conclusion, does this limit converge? The answer is yeah, it converges to something because the sum converged. So this is a way that you can go through and do infinite products. And really the way that you handle infinite products is you think about, well, let me take the log of stuff and do what you would do for infinite sums. So you have things such as, well, you need to have the terms go to 1 because you have the nth term test for infinite sums, and the log of 1 is 0, and these terms go to 1. Now, side note, do we know what this value is? Using the tools that we have so far discussed, no, we don't have what this value is. That being said, this is actually a very well-known formula. You can look it up, and there's actually some fun YouTube videos that go through and explain this that don't use very complicated math. So this is called the Wallace formula. It might be called the Wallace product. Yeah, let's change it to product. Wallace product. So what does it say? Well, it says that this number here, it's not just any number, it's a nice number. And you're like, ooh, nice number. So that must mean it's nice. Well, it is. And what does it turn out to be? It turns out, I believe, to be pi over 2. And probably weren't expecting that. Yeah, pi shows up in a lot of unusual places where it doesn't seem to have really any relevance. You know, why should pi show up? Well, you never know. You never know. All right, last one for today. Determine if the following are absolutely convergent, conditionally convergent, or divergent. And I'll go ahead and give you a hint here. You have one of each. So you have something which is absolutely convergent, you have one of these which is conditionally convergent, and you have that one of these is divergent. All right. So let's start. Okay. Well, we'll start with the first one. I mean, that seems pretty easy. We have negative 1 to the n. Downstairs we have log, log, log n. Now, there was actually a mathematician for a while whose email address was log, log. I don't know if he still uses the same email address. Probably does. Mathematicians tend not to change very much. So, log, log, log n. Okay. What do you think? Well, the negative 1 to the n tells us what? It alternates. So what happens to log, log, log? Well, the answer is if you're very patient, we know n goes to infinity. Log of n goes to infinity very slowly. So log, log of n goes to infinity really, really slowly. Log, log, log n goes to infinity like ridiculously super slowly. Like it just goes to infinity kicking and screaming the whole time. So this converges. And why does it converge? Well, alternating series test. Now, does that answer the question, absolute, conditional, or divergent? Well, we've now ruled out divergent because we've seen that it converges. Okay, so we're not done yet. Drop the negative 1 to the n. 1,000 to infinity, 1 over log, log, log. Converge or diverge? Well, here we can say, look, log, log, log of n, I don't want to try to integrate that or do anything. I just want to say, how quickly does it go to 0? Well, I can say that log, log, log of n is that it's a very small number. And in particular, it's smaller than n, as long as n is reasonable. You know, for example, I don't want to say 1 because log, 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 you have to wait till about like 40 or 50 before it even exists. This is always true. So what does that tell us? So that says that 1 over log, log, log of n. Oh, am I not using enough parentheses here? No, that's good. 1, 2. There we go. Is going to be greater than 1 over n. So in other words, 1 over n is smaller than this. So this would be bigger than if we start at 1,000 and went to infinity of 1 over n. This is the comparison test. Well, what do we know about that sum? This is harmonic. Now, this harmonic sum, it's just we start later, and therefore it diverges. Which means that this sum is really infinity. So, there's not a lot of room above infinity, so that says, lo and behold, this diverges. So, the original sum diverges when we drop the alternating. The original sum converges when we drop the alternating. It now diverges, and therefore our conclusion is this is conditional. Okay. Good. 1 down, 2 to go. The next one, n equals 1 to infinity, negative 100 to the n over n factorial. Now we're not going to belabor this too much. Really, what's the question? Well, the question is, what wins in the race between negative 100 to the n versus n factorial? And the answer is factorial is going to win. It's going to win like all the time. Factorial grows a lot bigger than exponential. It doesn't matter that it's 100. So the intuition says the denominator is a lot bigger than the numerator. And so we should expect it to converge. So usually it's the case when the denominator is much, much bigger. I mean, it's just, I don't want to, you got to be careful because things like 1 over n. But generally speaking, when it's like orders of growth faster downstairs and upstairs, it should converge. So we're suspecting it converges. And in fact, we're going to just skip right ahead to the absolute part, right? Because let's look at this sum, n equals 1 to infinity, dropping the minus sign, so 100 to the n over n factorial. Now let's do this properly. How do we show this converges or diverges? What's the right test to use? We don't want to use an integral test because of the factorial. Probably don't want to use the nth term test because that can't show if something converges. The nth term test only shows if something diverges. So we're knocking out tests. Comparison test could work, but it's a little bit hard to even limit comparison test. So it's either root or ratio. This 100 to the n, that's kind of saying, hey, try a root test with me. It's singing its siren song, root test, root test. But we also see what downstairs? We see that there's this exclamation mark. And when we see that, we know ratio test. All right, so let's just do the ratio test really quick. So we're going to apply our ratio test. And when we do that, what do we get? Well, this 100 to the n over n factorial, that's our a sub n. So we're going to take a look at the limit as n goes to infinity, a n plus 1 over a n. So that's the limit. N goes to infinity of 100 to the n plus 1. Divide that by n plus 1 factorial. That's the a sub n plus 1. Multiplied by the reciprocal of a sub n factorial over 100 to the n. Now, because we just did this, we should be really good at this. 100 to the n plus 1 over 100 to the n, what does that become? It becomes 100. Because you can cancel off a bunch of hundreds to the n's. The n plus 1 factorial and the n factorial, well, what you do is you pull off an n plus 1, And then after you do that, you'll have n plus 1 times n factorial, and the n factorials cancel. Okay. What's that limit? Well, upstairs, it's always 100. Downstairs, it's getting bigger and bigger and bigger, and that gives us a limit of 0. Now, what do we care about? Well, we care about how does this compare to 1. Turns out, true story, it's less than 1. So, by the ratio test, we know that the sum converges. That's our conclusion. So the ratio test, we got that the sum converges. So, that says that this sum converges. And that's the sum where we drop the alternating part. So, what's true about the original sum, where we did have the alternating part? Well, if the absolute value converges, then lo and behold, this will converge as well, and it's going to be absolute convergence. So there we go. Good. All right, which brings us to our last one. Now, let's look at this before we make a conclusion, and then we'll come back and say, wait a second, hold on. So, what do you see? There's a negative 1 to the n. Aha! Alternating, right? What happens to our terms? Well, you're dividing the inside 1 plus, and that part goes to 0, so you're going to log of 1, which is 0. So you alternate, terms go to 0. The conclusion is that the sum, you want to say converges. I know you do. I know you do. Oh, it's so tempting. It's so tempting. But you might remember, hold on. I said something. I said there were 3 sums, and I said that there's one of each kind. There's an absolute convergent, and we said this one was absolutely convergent. There's a conditional convergence. We said that one's conditionally convergent. So shouldn't it be, if there really is one of each kind, shouldn't this be divergent? Which means I can't have the sum converge. What's wrong here? Oh, something's happening. Oh, okay, what is it? All right, here, I'm going to go ahead and reveal the secret. This is sneaky. Now, what does that mean? Well, it means that we're trying to mislead you. We know what you know. And the reason we know what you know is because we taught it to you. But we also know you sort of have certain tendencies. You see certain things and you automatically assume. So when you see this negative 1 to the n, the assumption is what? Well, the assumption is that it's an alternating sum. But let's be careful here. Does it actually alternate? So let's take a look. And the reason that this turns out to be a little bit sneaky is this part right here. This cosine of pi n. Now, earlier today, we saw a sine event. And we said, the sine event, it jumps all around and it's not really easy to predict. But cosine of pi n actually is easy to predict. So let's think about it. So for instance, what would happen if we plugged in n equals 2? Because that's where we start, n equals 2. Cosine of 2 pi is 1. Plug in n equals 3. Cosine 3 pi, negative 1. Cosine 4 pi, 1. Cosine 5 pi, negative 1. So really cosine pi n, it's actually secret code for negative 1 to the n. So we hid an extra alternating sign. So let's see what happens here. So we have negative 1 to the n log of 1 plus negative 1 to the n over n. Now, we have to be careful here because there's 2 places where signs change. Do they cancel out or not? So that's actually not so obvious. But now we're going to do another quick fact. So, we did this a couple days ago, so this probably won't surprise you too much when we talk about it. Suppose we asked about the function y equals the natural log of 1 plus x. Now this function, it has an asymptote at x equals negative 1. So So it's coming off this asymptote. It actually passes through the origin, because log of 1 is 0, and then it slowly sort of like starts meandering. It's not leveling off. It does go all the way to infinity. It just takes its time to get there. Now, what do we see? Well, the next key observation is look at the tangent line at 0. If you do the tangent line at 0, it's actually not so hard to write it. You get y equals x. It passes through 0, 0, and the slope, the derivative of this function, is 1 at x equals 0. So the conclusion is, for small x, that we can say that log of 1 plus a small number is very close to just whatever that small number is. So as we look in the tail, in other words, close to the infinity, we see that this part right here, it's about negative 1 to the n over n. And remember, we still have this part here, which is very close to negative 1 to the n, because it's exactly negative 1 to the n. So when we put these things together, these two signs end up canceling out. So every term is a positive term. This is not an alternating series in any way. It's actually a series which has all positive terms. And the terms, as we get large, are approximately 1 over n. All right, now we're almost done, and we'll just sort of do a little bit of hand waving at the end to finish up. If the terms are like 1 over n, then what we would do is we would say run a limit comparison test, and the comparison would be with the series, the sum from 2 to infinity of 1 over n. Does this sum converge or diverge? And well, we've mentioned this before. In fact, just up here, this diverges. And therefore, by limit comparison test, this is a diverging sum. The original sum also diverges. So be careful. Be careful. Don't just, run into things, because even after you leave this class, you'll encounter unusual problems where things are written in a particular way to sort of, I don't want to say mislead you, but can catch you unawares. You don't want to do that. You're better than that. You're pretty smart. So, pay attention. Pay attention. Don't just assume that just because it looks obvious, you can just don't have to think about it. You should always think about every problem, because you never know when they're going to do something a little bit sneaky. All right. Well, that's it for this time. And next time, we make our next stop along our road. So we've finished our questions. When do things converge and diverge? So the next stop is, let's start talking about polynomials and infinite polynomials. It's good stuff, and we'll see you then. All right. Bye.